it's a question that is of interest to, I guess, everyone that is participating here, or most of the people that are in this workshop. So I will try to basically focus on in some aspects that cover a lot of several candidates of dark matter that are sometimes called alternative, and I will just try to go over them and maybe mention what are the key features of these candidates. So let me just start by saying that what we have so far is a theory. If we think about what is the purpose of say a theory that explains the formation and evolution of galaxies, then of course it's a theory that has to start from some initial conditions in the universe, let's say at the cosmic microwave background. So we have a early universe cosmology that can maybe give us an explanation for these initial conditions. But when it comes to the seeds that result in the galaxies that we observe today, the starting point can be something like the CMB. And then we want to develop a theory that takes us from the CMB all the way until the galaxies that we observe today. So what I'm putting here on this slide is just to say that we have now developed this theory that is mostly built upon what is called the cold dark matter hypothesis, which in essence is you can say it in two ways. If you think about, say, particle physics, then the idea is saying that when it comes to the physics of galaxy, this assumption would tell you that dark matter particles are made of classical non-relativistic and collisionless particles. And when it comes to another way of saying this is that when you integrate this assumption into say your whole structure formation model, then what you are really describing is, or saying, is that the only dark matter interaction that matters in this model, in this theory, is gravity. So you only put the gravitational interactions of dark matter, and that's it. The rest, of course, is what we call baryonic physics. So this is the physics, the complex physics of radiative cooling, hydrodynamics, star formation, supernova feedback, and so on. So there is a lot of complexity there that goes into structure formation model that is now built into these powerful supercomputer simulations that create these virtual universes like the one we see here. This is already relatively old. This is from the Illustris project, but it's essentially tell us that we have reached this stage where we can create these virtual universes that simulate more or less realistic galaxies. Now, despite this progress, I want to be clear that we still don't know what is the nature of dark matter. And of course, that's a fundamental question in cosmology, in astrophysics. And we don't know which are the masses of the dark matter particles, how they interact. And in this talk, I just want to concentrate specifically if this question is really true, if you really can say that gravity is the only dark matter interaction that matters. So I will try to focus on this talk, and I think most of the talks that we will be hearing in this workshop are around this idea. So now, just before saying that, this, of course, I think is clear, or at least it's clear to me, that there is no indisputable evidence that there is something wrong with this hypothesis. It's simply that there are other reasonable motivations to consider alternatives, like at the same level as we consider CDM. So specifically, I will be talking about two questions that are fundamental for, say, on our understanding of galaxy formation theory, and I will phrase these different other dark matter possibilities as trying to answer these two questions, or related to these two questions, right? So one is, what is really the physics that sets the minimum scale for galaxy formation? And the other one is, what is the physics that sets the central dynamics of galaxies? And I think these two questions remain open. And I would argue that it is within these two questions that maybe the possibility of new dark matter physics will appear. So this can be taken both as simply saying, well, we do not know the answer to this question, so it's important to consider all alternatives. And another maybe more optimistic take on this is because we haven't been able to find what dark matter is, it is important to answer these questions first to maybe we can find new clues about the nature of dark matter. So to be even more specific, I think these questions are potentially most likely going to be answered. This is just a guess. It doesn't have to be like this, but it's just a guess that these questions are perhaps going to be answered, or the nature of dark matter. If we can learn more about the nature of dark matter through the physics of galaxies, it is perhaps through dwarf galaxies. So these are, as you know, these are systems that are mostly dark matter dominated. And they have many much more dark matter than say baryons, than visible components, and that makes, in some sense, makes our life a little bit simpler because it means that the gravitational potential is mostly dominated by dark matter. So when we do all kinds of predictions and analysis and our understanding of these galaxies, this makes it a little bit less complex than more massive galaxies where the stars and gas can play a significant role and then, you know, mess up or confuse our interpretations. In some sense, we can then call them some kind of optimal dynamical detectors of, say, new dark matter physics. If you have a new type of dark matter interactions, maybe it is true, for example, that the stars in these systems that act as tracers of the gravitational potential that can give us a clue of new dark matter physics. So let me continue. I mean, this is a very busy plot, but I just wanted to put some kind of perspective on both the particle physics of this type of models that I will be talking about, and then also put it into the context of the astrophysics parameter space. How can one map the particle physics of a particular model into an astrophysics parameter space? So this is something I have been working on for quite some time, how this mapping works and so on. And it's, of course, very complicated. In some aspects, it can be model dependent, but I think in many ways we can try to do this mapping in a way that is useful for the physics of galaxies. So here on the left, you can see the particle physics parameter space of some of these models. Of course, there are many different ones that have different motivations for particle physics. There's the sterile neutrinos, the actions, you know, supersymmetric particles, and so on. And of course, in this particle physics parameter space, you might be interested about the mass of the particles and the type of cross section for interactions they have. But in an astrophysics parameter space, maybe you care more about some effective parameters that impact the physics of galaxies. So these effective parameters could be, for example, the scale at which this new dark matter physics impacts the formation of, say, galaxies, or the formation of halos, which are these dark matter structures that surround galaxies. So this scale is given in the axis, in the vertical, horizontal axis on the bottom, gives you kind of some scale in K for the power spectrum, but in the top it gives you some scale for the mass of the galaxy, of the halo. Whereas on the vertical scale, you have more like a measure of potential evolutionary effects or potential interactions between the dark matter particles, either with themselves or with other particles, that make it plausible that this interaction can contribute to modifying the structure of the galaxy. And it is within a parameter space like this in which you can take the particle physics models and map them into regions, like umbrella terms, that cover different models in which the new dark matter physics impact the formation of galaxies. So I will be using, you know, people use these umbrella terms a lot, and I will be using them also in this talk. Things like, of course, CDM encompasses all of these models in which no matter which particle physics candidate you have, it doesn't really matter for the physics of galaxies, as I said before. Whereas something like self-interacting dark matter, for instance, has these evolutionary effects because of the collisions of the particles that can impact how, the structure of the galaxies as time goes on. Or you have models like warm dark matter, WDM, in which the minimum scale of halos or dark matter structures that can form is affected. And you also have things like fuzzy dark matter, so dark matter that has kiloparsec scale quantum effects, or interacting dark matter, these models when dark matter can interact with non-relativistic particles to also produce so kind of interesting both evolutionary effects and also primordial effects. So I will be concentrating on try to give a little bit of flavor of each of these points in a way that uses these umbrella terms, and I will see how much I'm able to cover. Okay. Now before going into that, one could say, okay, you have this particle dark matter landscape, and you want to introduce this into our theory of galaxy formation and evolution. Of course, when you do that, you have to be able to also introduce the physics that we know is there at the scale of, say, dwarf galaxies. So I said I would focus on dwarf galaxies. So this physics is there, and it impacts the structure and evolution of these dwarf galaxies, even though I said it was reduced compared to bigger galaxies, but it's still there. And of course, we need to have a good understanding of these physical galaxies if we want to hope to disentangle it from say, dark matter physics. And I just want to mention here two effects that are quite important and that can have a significant impact on our interpretation. One has to do with how supernova, this is on the right, this cartoon, how supernovae, so when stars explodes, they can give energy, and that couples gravitationally to the halo, to the dark matter particles. There is a gravitational coupling that creates an impact in its evolution. So it can literally, puff up the inner part of the halo gravitationally and modify its structure. So if there is sufficient energy and the coupling has the right conditions, then this happens. It's a known effect. So you just have to deal with it. And another known effect is, of course, the physics of reionization. Once the universe becomes reionized due to the first generation of stars and galaxies, then there is this not only the reionization of the universe, but also the heating that is caused by this process. It heats up the gas inside halos in such a way that it doesn't allow it to cool down to form stars. So reionization sets already by this effect, it sets a minimum halo scale for gas to cool. So it sets a minimum scale for galaxies to form. The question is whether this minimum scale is just set by reionization or is also set by some unknown dark matter physics, or if it's a combination of both. So what kind of unknown dark matter physics I'm talking about that can impact the physics of galaxies? So the first one I want to discuss is just simply this effect that is called dark acoustic oscillations. So if you have a dark matter particle that can interact with relativistic particles in the early universe, then these interactions, it basically works in the same way as how photons interact with electrons in the early universe, in the early plasma at the time of the CMB, or just before the time of the CMB, to create this very well-known effect that is apparent in the CMB, in which you have this interaction between photons and baryons to create the baryonic acoustic oscillations. So this interplay between the gravitational collapse of the structures to try to form and the radiation pressure by the photons. So as long as this coupling is strong between electrons and between electron baryon plasma and the photons, then you have this balance between pressure and gravity, and that means that the fluctuations don't grow, they just kind of undergo this oscillatory phase. You can have exactly the same mechanism between dark matter and a new relativistic particle in the dark sector, or it could also be neutrinos and photons. And if you have this effect, then the end result is the same. You suppress the formation, so the gravitational collapse of small also small structure. Now, something similar can happen if you have a dark matter that has quantum effects that are significant. There, instead of the dark radiation pressure, what you have is some kind of quantum pressure, essentially the uncertainty principle that prevents your dark matter particles if they have a very, very small mass, right? So they have a large de Broglie wavelength, then this uncertainty principle essentially acts as a form of quantum pressure that doesn't allow the perturbations to grow at certain scale. And of course, you also have other type of dark matter candidates in which if they are sufficiently light, they become non-relativistic too late in the formation of the universe, and that also before that, right, when they are relativistic, they essentially cannot cluster, and this is the traditional free streaming damping, which is known for warm dark matter. So if you put these kind of possibilities together, I think what we have is something interesting here. So in this plot, I'm just showing the power spectrum on the vertical axis as a function of a scale on the horizontal axis. And on the left, you have the traditional CDM power spectrum. So this is basically the clustering as function of scales. Small scales have larger clustering, they collapse first. Large scales on the left could collapse later. Now, if you have some new dark matter physics, then you would create a cutoff in this power spectrum. So a new scale, a scale that is set by the physics of this new dark matter physics. So it could be, something thermal, like in warm dark matter, so the free streaming scale. It could be the sound horizon, because you have these dark acoustic oscillations, or it could be some kind of de Broglie Jeans scale set by the de Broglie wavelength, because there is some quantum effects at play. So all of these physics can be, we can give a hint of them if we are able to detect a cutoff like this one. Now, the other one I want to mention is that corresponding to self-interactive dark matter. So this is also a relatively simple effect in which you have dark matter particles in which they can collide with themselves. So here you instead of having something that is collisionless, like CDM, you have something that is collisional with itself. And it doesn't have to be very collisional. You just need one collision per particle, in average, one collision per particle in the history of the universe per Hubble time. And that's sufficient. One can show very quickly that that's sufficient to change the inner properties of the galaxies. So by changing the inner properties of the galaxies, of course, of the halos, then you change the properties of the galaxies as well. So it's a way to create an evolutionary effect into the center of halos that can potentially be observed. So this is, known as SIDM. So how is the structure in this kind of alternative models compared to CDM? Well, the large-scale structure is basically the same. This is what I'm showing here on the left, right? So this is a big simulation. So one of these supercomputer simulations that has only dark matter. On the upper part is CDM, the traditional model, and on the lower part, here is Colitos. This is a project that I'm not gonna talk about right now, but it's essentially dark matter that has self-interactions and dark acoustic oscillations. And something similar very, very similar we would observe if we were to observe warm dark matter. So the large-scale structure is basically preserved, and it has to be preserved because we know that a large-scale structure is basically CDM. But in the small-scale structures, when you look at the scale of halos, you start to see some differences, right? So whereas in CDM, you don't have a minimum galactic scale that can go all the way to very, very small masses that are irrelevant for the physics of galaxies. There is no limit to the phase space density that's again set by the thermal limit of the particle, which is very, very small, irrelevant for the physics of galaxies. Whereas in these other alternative models, you might have less structure because you have a cutoff in the power spectrum, and you have some thermalization of the inner halos due to the collisions between dark matter particles. So in particular, in SIDM, this thermalization I'm referring is something like this. So if you try to compare a CDM halo on the left versus an SIDM halo on the right, you can see clearly visible in these simulations the big differences. So the CDM halos are more triaxial, the collisions isotropize the orbits, and you create something more spherical that also has lower density. And here on the right, I think is nicer. Just this is I'm trying to present a lot of information in a condensed form to try to kind of get an overview. But here the bottom line or the main message for SIDM is that you start maybe with what you see here is a density profile. So you see the structure of the halo, its density in average shells, spherically average shells from the center. So this is a function of radius from the center out. So in CDM, you would observe something like the red line, the NFW profile. So very steep in the center, very dense and decaying towards larger radii. So this is in the density on the upper panel. On the bottom panel is a measure of the velocity dispersion, or if you want the temperature of the dark matter particles, the dynamical kinematic temperature. So in NFW, you get this bell-shaped behavior that is, again, easier to understand, and it has been known for CDM simulations for a long time. So the center is colder than the upper parts. But once you have collisions, then this behavior changes. And because collisions try to redistribute energy, then the colder part, which is, the parts that are colder in the center and more dense, interact with the surrounding regions that are slightly hotter and less dense, and they, try to equalize the energy. And this thermalization, trying to reach this thermal equilibrium because of the collisions, results in the formation of a core. So this green line that you see there. So a constant density, constant temperature core. But the collisions don't stop there, they continue happening. And because the surroundings are actually colder, we have this big reservoir of cold material outside and this hotter material inside, then the outflow now of energy goes from the outside in, and it's an irreversible process, and one can show that eventually this results in the collapse of the halo. So the collapse of the center of the halo, so this is the blue line, so the halo eventually becomes even more dense. So this is an interesting feature of SIDM. So all SIDM halos will eventually evolve into something, into a collapsed core that is denser even than the CDM halo. The question is the timescales for this to happen. Depending on the cross-section, the timescales could be much larger than the Hubble time or much shorter. And that's from several years now. This is one of the most, I think, interesting features of SIDM that people have explored. So the other one I want to discuss before this kind of now long introduction is that I want to discuss is just very briefly what happens in the case of fuzzy dark matter, just because I'm trying to cover this overview. In the case of fuzzy dark matter, as I said, because of the masses of the particles are assumed to be very, very small, like 10 to the minus 22 electron volts, then one can just quickly calculate what is the de Broglie wavelength for those particles, and it turns out to be like kiloparsec scale. So in essence, it just means that in the center of galaxies, you cannot you cannot cluster the dark matter more because of the uncertainty principle. So all the particles basically go into the ground state and form this kind of condensate, boson condensate in the center of the galaxy. Whereas in the outskirts, you basically have something similar looking than in the case of say standard dark matter. So that of course has some interesting properties that people have exploited and now have also created simulations with this fuzzy dark matter, as it's called, in which you have these effects that are basically quantum in nature. So the creation of these cores in the center, the soliton cores, that's the picture you see on the right, and also some interference patterns because you have basically the wave nature of dark matter at it's apparent at astrophysical scales just because the masses of these particles are so small. So all of these possibilities have been explored, and I just think due to this exploration, I believe I have maybe 4 minutes or so. So I will just try to say a few more words to basically introduce this challenge. I think we have this challenge in which we still don't know what is the minimum scale for galaxy formation. What can possibly set this minimum scale? Is it the physics of reionization that I mentioned earlier, which we know is there, but is it only that, or is it something else? Maybe some primordial dark damping that is connected to quantum pressure, or is connected to thermal streaming, or some interactions between dark matter particles and relativistic particles. And also the inner dynamics of the galaxies could be said by supernova energy, which this is something we know it happens, but it could also be due to the thermalization of the dark matter halo due to collisions. It could also happen because of quantum effects. Now, since I only have 3 minutes and I have a lot of other things that I wanted to say, that maybe I will have a chance if there are some questions about it during the discussion. I just want to end in the last 2 minutes or so with one specific effect that I think we could consider as important to distinguish these possibilities. So let me just go there. I had a lot here to say, but let me skip all this. I was too ambitious with this idea. So let me just talk about this one. So how you can possibly, I think this is the biggest challenge, how we can disentangle this possible dark matter physics from baryonic physics. And so in particular, I talk about supernova feedback. So I mentioned, okay, you have supernovae, you have the supernova explode and then inject energy into the into the surrounding interstellar medium, and through the gravity of the baryons as they expand through this energy, to this basically these blasts of energy released by the supernovae, these blasts create a gravitational coupling on the dark matter that can modify its structure. So what you see here on the left are observations of a galaxy, two galaxies, DDO 126 and DDO 43. And both of these galaxies are, dwarf galaxies that, if you plot on the vertical axis, basically the kinematics of the galaxy is like a rotation curve. Essentially is that. Then you see that these galaxies are consistent with a core. So they are consistent with having an amount of dark matter in the center that is considerably less than what you would expect from CDM only. So this very steep NFW would produce something like the dashed line, whereas the galaxies are clearly more consistent with something that is core. So how do you create cores? This has been a discussion for decades now. As I say, one possibility is to have this supernova feedback as creating the core. But I also mentioned that SIDM can create these cores through the collisions of self-collisions between dark matter particles. So back in 2021, 2022, we did this experiment. Can we create the same core, exactly the same looking, with these two effects? And the answer is yes. So this is what you can see here on the bottom left. So these are simulations that include baryonic physics, so include the supernovae, but include it in two ways. One is very efficient, so it produces a core within CDM, so that's the green line. And the other one is not so efficient, but it has a self-interaction, so that's the red line. As you can see, that basically these two cores would be indistinguishable, one from the other. One is produced by dark matter, and the other one is produced by self-interactions. So how do you distinguish these two cores? So we have basically degenerate solutions to the same problem. So how can we hope to distinguish that? And this is what I have been very interested in recently. a possibility is to use the nature of these two processes. They are different. They might give you the same core, but one is adiabatic, so slow, and another one is impulsive, the supernova. And it turns out that once you look at the details of the kinematics of the stars, one can distinguish these two processes by looking carefully at how these kinematics are. So if we have observations that are good enough, by looking at the kinematics of the stars, essentially the phase space of the stars, we see that if supernova is there, so they create the cores, then they create features in the phase space distributions, so like the shell marked here on the right panel. Whereas if you have something more like SIDM, you would observe something more smooth because the self interactions are adiabatic. So I will stop here, just saying that I think this, to me, this is exciting possibility to try to disentangle both, because I think we are in a situation where, at least when it comes to SIDM, we can have solutions that are degenerate between, baryon physics and dark matter physics. Thank you.
Thank you, Jesus, for keeping it also more or less in time.
Yes.
So I will restrain myself to ask questions, because all the questions are for later on. It was very interesting. I hope we can hear more in the discussion. Now let's move to Kohei. So Kohei Hayashi is, thank you for accepting the invitation, Kohei. So he's a researcher in the National Institute of Technology in Sendai, Japan, and he's gonna tell us about dark matter density profiles on galactic and subgalactic scales. So yeah, Kohei, the floor is all yours.
Okay, thank you very much for introduction. Can you see my screen?
Yes,
slide?
yes, we can
That's
see
good.
him.
Okay.
Great.
Thank you for inviting me this very wonderful workshop. So today I'd like to discuss the challenges that estimating the dark matter density profile of less massive galaxies and how to tackle these challenges. Okay. Yeah, let's go ahead. Okay, first of all, I'd like to say the main motivation.
Sorry, you haven't shared the screen yet.
Oh, really?
I see the screen.
Oh, yeah? Okay.
Yeah.
Sorry.
No,
Yeah, that was my mistake. Yeah, sorry. I'm seeing
Okay.
it now. Sorry.
Can it be good? Fine. Okay. Okay. Let's. Okay. So I'd like to say main motivation of the dark matter studies on less massive galaxies briefly. So while we are focusing on the small scales, so-called nonlinear regime here. Can you see the cursor? Okay. No.
Yes.
Okay.
I'm also seeing your mouse.
Okay. Sorry. Okay. So Lambda Kodak model is a remarkable successful at explaining a CMB and a large-scale structure of galaxy distribution on the spatial scale rather than 1 megaparsec MPC. But by contrast, on nonlinear scale here, it is unclear whether this theory, this Lambda CDM model, is in good agreement with observation or not. So one of the controversial issues on the Lambda CDM theory is, as you know, the core cost problem, the cost core problem. So I can skip this in detail, the core cost problem, but to resolve this problem, there are two most popular and promising solutions from the theoretical aspect. So one is the alternative dark matter model, such as self-contained dark matter and ultraviolet dark matter. So Savara already introduced this alternative dark matter model. The other is a baryonic feedback. This is also Savara already introduces. So strong and successive star formation history, stellar feedback from supernovae can transform the dark matter density profile from the to the core. This is one of the possible solution of the core cast problem. However, there are some systematic uncertainties in estimating diagonal density profile. So my goal, the goal of my studies are we really want to know how dark matter is actually distributed in the Milky, less mass galaxies, and what is origin of this dark matter distribution. This is my main goals. So today, I'd like to focus on the dwarf galaxy in the Milky Way. So, as you know, the dwarf galaxies in the Milky Way are the promising targets for studying the nature of dark matter, right? This is because these galaxies are very close to the sun, so we can do a detailed dynamical analysis using their resolved stars in the dwarf galaxies. And there are very low background sources, like a gamma ray and X-ray, something like that. So they are really clean target for the indirect studies. And finally, this is a very important point. These galaxies are really dark matter rich system, which means that we can estimate dark matter density profile based on the stellar kinematics. So regarding this study, dark matter studies using dwarf galaxies, let me advertise our recent work. So in order to constrain the property of the self-interacting dark, we focus on the self-interacting dark matter model. So we analyze the kinematics of the dwarf galaxies by incorporating gravithermal core collapse into the self-interacting dark matter models using semi-analytical sub-Haro models, so-called sashimi SIDM. So left panel shows sub-Haro number distribution in the Vmax and Rmax parameter space for CDM and the SIDM model. Okay. As you can see, at the fixed Vmax, like 20 kilometer per second, around here, right here. Okay. SIDM sub-halos are more widely distributed, right, than the CDM halo, like here. Okay. Here. So because gravithermal collapse, it happens here. So using this distribution as a prior, we can calculate the line outside velocity dispersion profile for these sub-halos, like this one. The right figure shows the right side velocity dispersion profile from the observation data for Fornax, one of the classical dwarf galaxies, and right side velocity dispersion profile from the sashimi SIDM prior for sigma over m equals 0 and 10 and 100 respectively. So sigma over m equals 0 correspond to the CDM, like a CDM prior. Correspond to the CDM prior. So the prior with sigma over m is 100. Okay, here this green band in the right panel. So as you can see, this prior is broader and higher left side velocity dispersion profile rather than the others. Okay, like a 10 single value called 10 or 0. Okay. So this is because gravitational collapse happens around this regime, which means sigma over m around 100, the gravithermal collapse will happen. That's why the line side velocity dispersion is yield wider and higher values rather than the other one. Okay. So using this prior of right side velocity dispersion, we calculate alteration of the self-intact dark matter to the CDM cold dark matter for each terrestrial galaxies. So this figure, two figures show the alteration as a function, alteration of the as a function of the sigma over m. Okay. The values of alteration being greater than 1 here. This means dual galaxies prefers to SIDM model. Okay. On the other hand, the alteration being the lower than the 1 around here, which means the dual galaxies prefer to cold dark matter model rather than SIDM model. Okay, and this solid black solid line shows the estimated alteration for all ultra-fine dwarf galaxies and classical dwarf galaxies. Okay, it's all combined model. So as you can see, the results reveal the bimodal feature like here, bimodal preference for small and large cross-section and dual galaxies, ultra-fine dwarf galaxies. On the other hand, the classical dwarf galaxies show the gradual decline in the alteration as cross-section increases, like this here. Okay. And finally, this figure shows the contour plot of the alteration with a combination of the ultra-fine dwarf galaxies and the classical dwarf galaxies result. From this figure, we can say that the dwarf galaxies prefer cold dark matter model to self-intact dark matter model with scattering cross-section around here, this blue region, Blue region means the dwarf galaxy disfavored self-intact dark matter model here. On the other hand, around here, okay, still sufficiently acceptable if self-intact dark matter still sufficiently acceptable if velocity dependent cross-section is assumed. Okay. This is my our preliminary result. But on the other hand, there are still large space here that favors self-intact dark matter. This red and the orange region here is still CDM favored region. So in order to gain the insight into the nature of dark matter from the galactic dual galaxies, so it is necessary to place more and more tighter constraints on their dark matter density profile. However, there are still large uncertainties on dark matter density profile of the dual galaxies. This is because there is systematic uncertainties from the model assumption. And so for now, we only have the limited kinematic information. So here I'd like to discuss how to overcome such challenges. First, I'd like to discuss the systematic uncertainties from model assumptions. So when we assume the spherical symmetry, we can easily calculate the line-of-sight velocity dispersion profile from the spherical Jeans analysis right here. But however, the velocity anisotropy, like this one, and the dark matter density profile are completely unknown. This one. Okay, so we need to set free parameter to make attempt to constrain this free parameter from the observation. Okay. However, as you know, in this technique, which means the spherical Jeans analysis, there is a strong degeneracy between the velocity and entropy parameter and the dark matter density profiles, because we only have a line side information. So in order to break this degeneracy, we have some prescription to break this degeneracy. So one is we can use the higher order velocity moment, not only the velocity dispersion but also more higher order moment. And the second one, we try to get additional kinematic information. And the third one is we try to relax the spherical symmetry assumption. Okay. First, I'd like to introduce the new dynamical model considering the higher order prime stability moment. So to do this, my collaborator, so Dafa Waldner, who is a PhD candidate at Tokyo University, he developed the dynamical analysis concerning the higher order velocity moment, which means we consider the non-Gaussianity of the line-side velocity distribution. Okay. So first, I would like to show the power of the force of the moment, higher order moment, through the mock analysis. So this figure shows the posterior distribution of the gamma, which means the inner slope of the dark matter density profile, and the velocity anisotropy parameter. Okay. Velocity anisotropy parameter estimated from our analysis with only 500 stars with 2 kilometer per second velocity error. This result comes from the second order velocity moment only, which means the only velocity dispersion profile only. Okay. On the other hand, from this figure, the combination between the second and the fourth order velocity moment, okay. Sorry, right panel show the combination between the second and the fourth order velocity moment analysis with the sample of the star is about 5,000 with 2 kilometer per second velocity error. Okay. Okay. As you can see, okay, this combination between them can break a degeneracy between the gamma and the beta anisotropy here, right? And we can improve the estimation of the dark matter density inner slope. I mean the gamma here. This is one of the main results. But on the other hand, in order to constrain the dark matter density inner slope, the large number of the velocity data sample should be required. Okay. Okay. This figure shows the estimated dark matter density profile by second order velocity moment only, and combination between the second and the fourth order moment from mock data with different data sample, 5,000 or 500, and different velocity error, like a 2 kilometer per second or 0.01 kilometer per second. Let's focus on the left panel here. So even though we have 5,000 kinematic sample and very small velocity errors, okay, there are still large uncertainties in the dark matter density profile at inner part, okay, estimated by the second order velocity moment only here. But on the other hand, the fourth order moment will help to improve the estimation of the inner dark matter density profile at the inner part here. So this is quite different using or not using the fourth order moment or not. Okay. So this is one of the let's say in the way of the overcoming the challenges. However, I'd like to say that we need to consider the effect of the contamination stir, okay? Because non-Gaussianity of the line side velocity dispersion are really sensitive to the shape of the outer skirt here. So, but in this analysis, we do not consider the contamination effect of the contamination star. So the next step we need to consider the such effect. But this higher order velocity moment should be essential for improving the dark matter, estimating the dark matter density profile. Okay, I'd like to move on the second presentation. So to break a degeneracy, we need a large number of the stellar sample and new kinematic information. Okay. First, I'd like to introduce a new spectroscopic spectrograph attached to the Subaru telescope, so-called Subaru prime focus spectrograph, Subaru PFS. So PFS have the very wide field of view, about 1.3 degrees as a diameter, and they have very massive multiplicity, which means they have about 2,400 science fibers. So which means that we get stellar spectroscopy a lot, I would say. A huge number of the spectroscopy, stellar spectroscopy from the Subaru PFS. So this Subaru PFS science operation will finally start from this February. Okay, finally started. And the PFS Subaru strategic program, as I say, PFS SSP survey has 3 science pillars. One is cosmology and galaxy evolution and galactic archaeology. So PFS has the widest field of view among the current optical multi-object spectrograph, such as the Gemini and the Keck and the BLT frames. As you can see, the PFS is quite a huge field of view rather than the other current spectroscopic survey. Okay. So owing to the prime focus of the Subaru telescope, PFS will enable us to do the very wide and deep spectroscopic survey. And thanks to our wide and deep PFS survey, it will enable us to get huge number of stellar spectra in the wide area of the galactic dwarf stellar galaxies. So for example, this left figure shows the sky distribution of the stars around the Ursa Minor dwarf stellar galaxies taken from the Subaru hypershaping data. So PFS can cover the whole region of the Ursa Minor dwarf stellar galaxies only 4 pointing, basically only 4 pointing. But we have additionally 1 pointing. Okay. In total, 8 pointing, we can cover the entire region of the Ursa Minor dwarf galaxies. From the end-to-end simulation, observation simulations, this 8 pointing, we do observe over the 5,000 stellar spectra of the member stars. So for now, we only have the about 300 stellar spectra, but the PFS will get 5,000 stellar spectra of the member stars. So this is kind of the revolution of the dwarf stellar galaxy spectroscopic survey. So this is the current status. This is the current Subaru PFS dwarf spheroidal survey plan in Subaru SSP. So we will observe the 6 dwarf stellar galaxies and 1 dwarf irregular galaxy. So the red hexagon in these panels, in each panel, I indicate the pointing that will be repeated repeat observation to determine the binary stars. So in total, small PFS will observe the dual galaxies at the 25 nights, correspond to the 72 hours, okay, on SSP. So based on such survey plan for dual galaxies, we are also investigating how much PFS observed can improve the estimated dark matter density profile using the mock data sample. So we try to estimate the mock dark matter density profile from the non-spherical analysis with current small data. This pink dot, pink one, and the PFS forecast is the purple one. Okay. From this figure, the PFS forecast can reproduce, okay, widely reproduce the dark matter density profile rather than the current small number of data. So based on MOX analysis, PFS will enable us to recover the density profile. So that means the large data volume over a wide area by PFS observation can recover the dark matter density profile precisely. Okay, second one, I'd like to introduce the very important works for new climatic studies of the dual galaxies. So Virtual 2014, 2024 analyzed the full epoch of the Hubble Space Telescope imaging over about 20 years for Draco dual galaxies. So they measured proper motion for about 360 stars and combined then with existing line side velocity data to obtain. And for the first time, they resolved 3D velocity dispersion profile right here. This figure shows the line side velocity dispersion and the dispersion profile of the proper motion here. Okay. And they presented Draco dual galaxies has a Caspi dark matter density profile consistent with the other previous studies like this one. Okay. This is the best fit profile from this 3D velocity dispersion profile. Okay. However, this results still large uncertainties on the dark matter density profile, even though they use the 3D velocity data. So this is because the number of data is still not statistically sufficient to constrain dark matter density profile. And Hubble Space Telescope HST pointing are really patchy. I mean, the only two pointing to get the proper motion data. Okay. So, I'm now preparing the proposal, the observation of the dual galaxies using Nancy Grace Roman Space Telescope. This is because Roman telescope can cover the much wider region of the dual galaxies than the, of course, HST. Okay. This is a really large field of view of the Roman Space Telescope, and Roman can observe the proper motion of the individual stars in the dual galaxies. And this figure shows according to the reader 2021, so they conclude about 1,000 proper motion data will break the degeneracy between the gamma and the velocity entropy, and they said proper motions, large number of the proper motion data can robust estimate of the dark matter density profile. So that's why I try to prepare the Roman observation proposal. So, and I'd like to introduce the synergistic observation between the Raman Space Telescope and the SBIRC PFS. So because its large field of view and the high precision photometry of the star, Raman will enable us to measure the proper motion of the individual stars in the dwarf galaxies. For example, the provided typical internal velocities of these stars are about around 10 km per second. So we expect the proper motion of 0.03 milliarcsec per year in dwarf galaxies at the distance of the 70 kpc from the sun, like Draco dwarf galaxies. So this can be achievable with Raman astrometry over only 5 years. So combination between the Raman and the SBIRC PFS will get a large number of the 3D stellar motion of the individual star in the Milky Way towards the galaxies. So this means I want to say that this synergy will provide a new stringent constraint on the dark matter density profile of the dwarf galaxies, and then provide a new insight into the nature of dark matter. Okay, so maybe about 5 minutes or so. Maybe it's time. Okay, the last one, I'd like to introduce the relaxed spherical symmetry assumption, but okay, I will skip in detail. Maybe it's almost up, I think. Yeah, okay, I skipped the. This is my main work on the dwarf galaxies studies. So I developed the non-spherical dynamical mass model to set constraint dark matter density profile. This is because such a non-spherical dynamical mass model can mitigate degeneracy between the inner slope of dark matter density profile and the velocity analysis parameter, like here. So this is quickly a review of my result. So this is estimated dark matter density profile from the non-spherical dark matter density dynamical analysis. So for the classical dwarf galaxies, like here. So for example, Draco, the smallest galaxies among the classical dwarf galaxies, has favored the Caspi dark matter density profile, like here. Okay. But on the other hand, like Fornax sculptor dwarf galaxies, like favor to like less Caspi density profile, like here. So I mean this means I can say that there's a diversity of the dark matter density profile in the dwarf galaxies. Okay. Sorry, maybe time is up. So, okay, finally, summary of my talk. So, the galaxies, especially for the dwarf galaxies, are the ideal target for studying the basic property of the dark matter particle. But there are still large uncertainty in the dark matter density profile of the dwarf galaxies due to the model assumptions and the limiting data. Okay, but in order to overcome such challenges, SBIRC PFS enable us to obtain the large number of stellar line sight velocities out to their outer scope of the dwarf galaxies, and Nancy Grace Raman Space Telescope will also enable us to measure the proper motion of the individual stars precisely. So in the future, synergy with this new equipment will provide a large number of the 3D stellar motion of the individual star in the dwarf galaxies, and it will, I hope it will allow us to place a stringent constraint on the dark matter density profile. Okay, sorry, that's it. Thank you very much.
Thank you, Kohei. Nice work. Also, I would like to ask you many questions about
Okay. Thank you.
how your work on the high velocity moments compare with those of Justin Reed also, but let's chat later on.
Okay. Sure.
Thank you. So now let's
Thank you.
move on quickly. We are not on time. To Blom. I'm not sure if I'm pronouncing your name correctly. Sorry. So Fir, can you hear us?
Yes, I can hear. Yeah, it's correct. Thanks a lot.
Great. So, well, you are the next speaker. Fir Blom is from Weizmann Institute of Science in Israel, and he will tell us about gravitational dynamical proofs of the nature of dark matter. So, yeah, we can see your slide.
All right. Thanks a lot, Maria, and organizers for this invitation. It's been really interesting so far. I'm not used to giving a seminar without questions, but I'll do what I can and hope to discuss the questions as you suggest.
Questions are at the end.
Exactly.
So, which is, we will break for 10 minutes after your talk and we will recombine in another discussion session. Sorry
Sounds
for
good.
the interruption.
No, it's just a format for people with a long memory, not for me. That's the problem. Thanks a lot. All right, so I would talk a little bit about dynamical probes of the nature of dark matter in galaxies. This is supposed to be a 30-minute seminar, so it's not going to be really a review, just a discussion of mostly pretty much, I would say, 1 or 2 points that I would like, or results that I would like to point out to by our group and by several other groups in parallel. And then if I have time, I'll discuss some other results. So really not a review, but just a look at some particular thing. Just to start it off, as we all know, so there is very strong evidence for dark matter from galaxies and from cosmology, but of course we don't know what it is. One thing that I find important, one thing that guides at least my attitude on this problem of dark matter is the fact that, the mere fact that we have, or we think we have, a lower limit and roughly an upper limit on the mass of dark matter particles is a result of what we can do from gravitational considerations alone, without turning on any non-gravitational interactions of dark matter. This doesn't say at all the dark matter doesn't have non-gravitational interactions. If I need to guess, it has. And maybe it's not, maybe it's quite as complex and complicated and interesting and diverse as the our sector, baryonic sector, is, with all kinds of particles and their interactions. Nevertheless, the minimal set of assumptions we can make would be just to look for gravitational probes. After all, the reason we think there is dark matter is based on gravity alone. And so this is why I restrict myself to this scenario. Of course, if we're lucky and there is some significant non-gravitational effect, this would be spectacular and very worth studying. And so what we know about dark matter in galaxies is usually can pretty much be defined as kinematical information. We had a great example of many related discussions and analysis in the talk by Kohei. And the idea here is that we look at a galaxy, be it dispersion-dominated galaxy or maybe rotation-supported galaxy, and we try to understand the phase space distribution of the stars at the snapshot of time at which we look at it. We measure the distribution and velocities, and we ask ourselves, well, the simplest question, so you can never really sequester dynamics. The way you try to sequester dynamics is to imagine to yourself that the system is roughly in statistical equilibrium, and therefore my snapshot with enough stars gives enough information to understand what's going on. Okay, so you need to invoke an assumption, often rather reasonable, sometimes maybe questionable, about equilibrium or statistical equilibrium of the system. This is what I would call kinematic. So there is this assumption in the background, and the information about dark matter from galaxies almost always makes these basic assumptions in the analysis. There are additional, of course, constraints from kinematics. And what I was highlighting here, these two papers randomly selected, one self-promotion, but there are many other works you can find there, and another by this group, which is one of the first to study mixed models of this idea. These are constraints on ultralight dark matter. So over here in the low end of the possible range for dark matter. So analysis like these and many others along similar lines have established, the way I can see it, and we can justify it quantitatively, they have established this lower limit of order 10 to the minus 21 electron volt. And as usual, because this is the limit, in a way it's the frontier, everybody is fighting about the details of this limit. Is it a factor of a few maybe lower, or maybe even possibly a couple of orders of magnitude higher, right? So this is a very logarithmic axis, or our uncertainty is logarithmic if you want. We are fighting over orders of magnitude sometimes, but there is progress, I would say. And it's related to this end of the dark matter, possible dark matter mass spectrum that I would like to discuss dynamics. And so those analyses I mentioned before are essentially kinematical. Certainly the galactic constraints are kinematical, again, looking at rotation curves and so on. But in last few years, these constraints, maybe decade, these constraints have been pushed forward, and now there are claims, and I would say there is some evidence that in fact we can push this lower limit all the way up to around 10 to the minus 19 electron volt. Again, the details are being contested. I'll speak about some of these. Quite generically, in these situations, the line of argument or the analysis is actually dynamical. Okay, so the information is not coming just from the current snapshot and assuming equilibrium. It's coming from looking at the data we have, which is always a snapshot. What can we do for, at least for low redshift systems like this? And asking ourselves what kind of past evolution, past dynamics could have led naturally to the situation of the systems as we see it. Maria, do you also see my cursor?
Yes.
Awesome, thanks. And so the stronger limit currently quite generically coming from dynamics, which is interesting, and to a certain amount, a certain extent, a shift in the direction of these studies. I should say, so restricting ourselves to gravitation alone doesn't mean that in terms of the array of observational systems or observational data, different systems that we can look at on, it doesn't mean that we're very limited here. There are by now probably dozens of different observational systems or different systems we can observe in cosmology and in astrophysics. This is just a small selections of examples that are dear to my heart, but there are more. There are several examples by now of gravitational lensing analysis that are sensitive to dark matter. They come from gravitational lensing in the region of supermassive black holes, strong gravitational lensing of galaxies. Of course, microlensing has been a traditional analysis, very important here at the high mass end, and weak lensing and many, many others, cosmology, and of course, many types of galaxies and many different analyses there. And in many of these, dynamics also make an impact. If I have time in the end, I will comment about how some of these other analyses can even extend the reach to lower masses. So I do this in blue. This is below what I call the lower limit on the mass. So here, I mean, we can probe even some small fraction. If even some small fraction of dark matter is made of a very light particle, it cannot be all the dark matter because of other constraints, we could still see it. And theoretically, this can be very interesting and worth looking at. Okay, so let me go to the point that I wanted to make. And so this is about fuzzy dark matter or ultralight dark matter here on the top left. And it's the basic idea was mentioned by both speakers before me. It's this idea that if you look at dwarf spheroidal galaxies, neighbors of the Milky Way, then there is some evidence that these galaxies may share a similar central density in their centers. It's also very interesting to ask what defines the smallest dwarf galaxy systems that we see. I'll comment about ultrafaints towards the end. These are the classical dwarfs. And they also share some similarities in terms of characteristics, scales, that define at least the stellar population. And these scales are actually the velocity dispersions and the scales that is central densities all seem to be roughly compatible with what you expect from ultralight dark matter if the mass of the particle is around 10 to the minus 22 electron volt. As most of you probably know, there have been numerous analysis of this. This is a tiny little sublist, less than 10% by far of all the works that try to explore this idea. So what do we have? We have these astrophysical systems. Kinematics give us potential clue that maybe ultralight dark matter explains what looks like maybe a repeating property. I don't know if fundamental, but the repeating properties of these objects, they share these central densities to some extent. Maybe this explains it. Now, to recap past result, also probably most of you know from kinematics, well, this idea of the central density, also mentioned in the talks before me, is that a dwarf like Fornax and the other dwarfs, possibly the entire stellar population is essentially embedded inside of what is called as the central core of the soliton solution. It's actually more closely related to an oscillon, but the central distribution of ultralight dark matter, which can naturally, if the mass is 10 to the minus 22 electron volt, its size will naturally be comparable to the entire stellar body. And then it would provide a core and some cutoff or define and if you want, universal density profile for these dwarfs. So that would have been a beautiful possible explanation of the structure of these dwarfs. Now, here is the thing about astrophysics and kind of like, if you want, there is an analogy to particle physics or to the Large Hadron Collider, for example. So at the LHC, if you have some anomaly or some intriguing measurement that appears in one detector, for example, Atlas, luckily it's particle physics. We've built another detector, CMS, and you can check, does CMS see it too? In astrophysics, if we're lucky, if we're working on the right set of phenomena, there would be the equivalent of this. So here, the way I see it, there was a signal from dispersion-dominated dwarfs. Well, there are many other dwarfs, like low surface brightness disk galaxies, that are similar in the dark matter content we think they have, but the stellar distribution looks very different. So disky, low surface brightness dwarfs with a lot of dark matter. Essentially, in this particular galaxy, the dark matter to stellar mass ratio is quite comparable to Fornax, almost everywhere in the galaxy. And so it's natural to ask, if Fornax is explained by this kind of core, can we find this core in the other experiment, in CMS, in other types of galaxies, right? The answer is we don't. In general, this is widely agreed. Many analyses looked at this independently. There are, of course, systematic uncertainties. You have to model the gas profile. You have to understand what you're seeing. Are there warps? Are there kinks? And so on. How well do you understand this rotation curve? And so it's good that many people looked. And the point is, this 10 to the minus 22 electron volt, the same numerical simulations of galactic halos with ultralight dark matter that claimed to explain Fornax and its neighboring dwarfs, they would predict this kind of velocity feature in this particular rotation-dominated galaxy. There is a large uncertainty, but even within the uncertainty, this prediction is way off the curve. And so what I want to emphasize at this point that I like is, first, well, we don't see it. I would say we've ruled it out, or Atlas and CMS don't agree. Take a step back and think what's going on. On the other hand, just imagine, right? This could have been spectacular. Just imagine this is the way those rotation-dominated dwarfs look like. We would all be, dancing in the streets. And so astrophysics has the promise to give you potentially robust detections. This case, it didn't work out, but combine the information. And just to mention, of course, there are many systems like this. You can repeat the experiment in the sense. And so if you look at many other mostly rotation supported, mostly dwarf galaxies, you can slash the databases as you wish. There are quite enough systems. And most of them don't show evidence for rule out this inner core in the distribution of dark matter. So in this plot, the y-axis is the ratio of the core mass predicted in this ultralight dark matter model, the ratio of the maximal mass allowed to the predicted amount of mass in that core. And the x-axis is the mass of the particle. And you can see in a wide range of m, you would naively think that there should have been an effect, and we don't see it. So at least this prediction of the amount of core mass predicted by the simulation, this is in strong tension with observations. Many other people looked at this. Recently, also the group at ISC looked at this, and they took a slightly different attitude. They tried to fit how much core mass can there be there. And so, for example, they noticed that around 10 to the minus 23, you can get a great description of these LSB galaxies. However, even there, the amount of mass that you need, or core mass that you need, is significantly below the relation. So it would be somewhere here. Here you can describe the system. This was in the first talk. And indeed, we don't really understand the slope, the fact that these inner rotation curves seem to be consistent with constant density, or want a constant density core. Either way, this doesn't look like ultralight dark matter. I should say, so the question of how much soliton mass, how much core mass there is, this is certainly a dynamical question. It relies on understanding, is it sensible, or do we expect that an ultralight dark matter halo would develop dynamically the soliton core in the center of it, supposing, for example, it wasn't there in the beginning. So is it a robust prediction? There is a raging argument about this in the literature. However, if you look a little carefully behind, read the abstract below the title, or look at the plots, this whether there is or there isn't, on how robust is this soliton-halo relation, you find that most of this argument is about a factor of 50% correction. So in fact, it seems to us, to my group, and I think this is, just look at the literature, you'll see it, that simulations robustly agree these cores form in galactic-like environments. Maybe in very clean situation or just two-body collision, you can have more complicated situation, but in most stochastic galactic-like situation, you form these cores. And I think, so this is very robust. I'm very happy to discuss it if you want. So this is from a recent paper, simulations by Luca Teodori, a student here, who is looking at, in numerical simulations, at the evolution of these cores. The thing to look at in this particular plot, for example, that I'm putting my cursor in, what we're plotting is the following thing. So this is a galaxy, if you want. This is information related to a Fornax-like system. As a function of time, what Luca is plotting is in blue, the characteristic radius of this soliton core that he's finding in the simulation. And in the dashed blue, he's plotting the predicted soliton core halo from the original references. When the radius is below the prediction, it means that there is a bit more mass. The effect is a bit larger than expected, but notice that there is some discrepancy. It's at the level of tens of percent. Tens of percent are very far from saving you from the observational constraint on the systems in low surface brightness galaxies. Okay, so this seems to be robust. We do see something that was anticipated long ago, and we can estimate, we understand there is an analytical argument for why this would be, that as you push the little m, the mass of the dark matter particle, to larger value, right? So as you try to see how sensitive we are to little m, ultralight dark matter particle mass in this region, then the formation or the dynamical time to form this soliton core grows, it becomes longer. So this is an example, a similar system to this. This is again the radius of the core. The smaller the radius, the more mass you have in the core. This is the naive prediction calibrated on or produced by simulations for this little m. And you see that as the mass of the particle becomes larger, you form less. So the radius of this core is larger than the naive, if you want, static expectation by a bit, because it didn't have enough time to form. We understand this. And so this means you can't and you shouldn't, and we didn't, and I don't think people did, generally, push results or constraint at 10 to the minus 22 all the way up to larger masses. You got to test it. There is dynamics in here. You got to test that the dynamics is right. The dynamics seems to be right, certainly up to about 10 to the minus 21 electron volt, as far as we can see. Let's skip this. But now I take a step back and let's go back and think about dynamics rather than just kinematics, again, for Fornax. And as I said, and as most of you know, again, the fuss about fuzzy dark matter came from kinematics, from the fact that the rough scale and velocity dispersion of Fornax-like systems seems to be very nicely compatible with this ultralight dark matter at 10 to the minus 22 electron volt. But that was just a snapshot. What happens when you start to think about dynamics? So if you place a system like Fornax here, in particular, if you place the stars, the stellar system, in the phase space that your GINS models tell you they seem to be in, right, or that your static GINS analysis says you should understand, you actually find that in this ultralight dark matter model, you don't stay static. GINS analysis breaks down formally. The breaking down is a slow process. So basically at any instant in time, over some dynamical times, the distribution is not far from static GINS analysis, okay? However, it evolves in time on timescales of hundreds of millions of years, so less than a giga-year. And that's what Luca and Andrea here in the pictures are showing in this plot. So the red curve here now, if you look at it, this is the characteristic radius of the stellar body of Fornax, a Fornax-like simulation. And over here now, depending which exact stellar distribution you look at, this is an example of a stellar distribution we are focusing on for the properties of it. And so the gray shaded band is roughly the observed half-light radius of the stellar distribution. Now you can fit the stellar distribution instantaneously with a reasonable description by a GINS analysis. But if you let the system go, you actually find that it evolves. It does not want to stay. It actually evolves and saturates at values of half-light radius that is larger than what we see. To understand how significant this is, so if here is the circle roughly describes the half-light radius of Fornax as described by this measurement, this is what we think, I mean, the system will evolve into. So you can fine-tune in a way your solution, but it doesn't stay there. There is fine-tuning, there seems to be fine-tuning involved in this. So my take on this is that the original kinematics interpretation of data from Fornax was, in fact, we were all totally in a way interpreted wrongly, or we missed the dynamical information. So I need to wrap up. Well, so this dynamical information with Fornax and some other galaxies, we think one can push the limits all the way by a factor of order 10, above 10 to the minus 22. This is again from these dwarf spheroidal galaxies. These limits are consistent with detailed kinematical assessment, similar to what we heard from the previous speaker. All of this, both the dynamical interpretation and the kinematics have systematics. There is a lot of work to be fully convinced that we're not missing something important. But this is just to say our constraints are consistent with kinematical constraints when they look in the details. And they're also consistent with stronger constraints from kinematics that other groups have derived based on ultra-faint dwarfs that have stellar bodies like nuclear star cluster that are much, much, much smaller, a factor of 100 smaller or so, or a few tens smaller than the size of Fornax-like systems. I would agree that these UFTs and their stellar clusters are very sensitive and interesting probes of dynamical evolution. Of course, the question is how well can we understand the systematics here? I want to highlight also that these small systems and UFDs in general can offer many exciting puzzles and keys. I think it's fascinating to look at them. So there is a group at IAC that has been pointing out that the distribution of these UFDs is very puzzling. Some of these puzzles actually, once you think on it, carry back to Fornax. Happy to discuss in the discussion sections. But I think this is a fascinating front to consider further, both for constraints and maybe for hints on what dark matter is. Okay, I think I'm almost out of time. So I will just mention in a word about another direction we can take this dynamical analysis to. And so, as I said, there are many other ways to think about gravitational only probes of dark matter. This is an example using strong gravitational lensing and lensing time delays with an effect that I call action edgenography when Luca Teodori doesn't stop me from saying it. Now he cannot. That's great. He's muted. He can't do anything about it. So I call it action edgenography. And the point is that is the following. So if we actually happen to have even a small contribution to dark matter coming from a very light particle, so it cannot be all of the dark matter, then even a relic amount of order 10% in relic density coming from the ultralight axon, actually we predict that it should have a subtle but interesting effect in measurements of the Hubble constant, H0, using time delay cosmography. The logic for me, from the theoretical point of view, is what we're looking for. Well, we're not solving the dark matter problem. This is just a small amount, but we are hunting for Axiverse states. So if there is some ultra-light dark matter particle, it's kind of natural theoretically to think there are many others. Well, now we're telling you all those many others cannot be even 10% essentially of the relic density, because there will be an observable effect. Just to flash the result, basically what these ultra-light dark matter do, they form flattened cores in the center of the galaxies, and even 10% effect in the total density around the Einstein rings of these systems. I show here similar typical regions of the Einstein ring can cause biases in the inferred H0. So the numbers in blue are bias in H0, and this will be extremely difficult to see, we think, from imaging distortion. So the first way you will see it, if there was 10 to the minus 25 electron volt particle, and it was 10% of the dark matter in the universe, the first way you may see it is by a small bias, positive, by the way, bias in H0, currently consistent with data. Is this the explanation? I don't know. It's not necessarily my bet for the H0 tension related to time delay measurements, but it could be. And it would be very natural from this point of view. These models will just do it. So I'll skip the details just to show that in this paper, what Luca has been able to do is to simulate these halos and show dynamically that we really do make these flattened blobs, and confirm that we think the effect is there. Okay, I will wrap up on the interest of time. Just to say that I left in the backup a discussion about dynamics of globular clusters, and there are many other examples I can talk about. All right, Maria, thanks. I think I'll stop here.
Thank you, Phil. I think we can still dance in the streets, despite nature not being
Fantastic, I agree.
as easy as our equations. And I think you can also give the power to Luca to talk. But okay.
Oh, I can? Okay.
I think so, I think
didn't
so.
know.
But maybe let's leave that for the discussion. We're gonna stop now for 10 minutes. Unfortunately, we are not providing coffee. Next time, maybe. And so let's recombine in 10 minutes. Please note that we are gonna be in another Zoom room that you will have other rights. Okay. So in any case, it was very nice to see all of you, and I hope many of you will join us later on.
So with the, what do we do with the Q&A here?
With the
That way-
Q&A, I have taken snapshots, and what I
and we
was thinking
paste
is,
them.
I was thinking on pasting them, but
You
yeah,
can paste directly the snapshot in.
exactly in the Padlet.
Okay,
Okay. So okay, see you in 10 minutes.
thank you.
Thank you. Ciao.
Thank you.